So in the previous video we talked about self-attention with learnable weights. Let's now go from self-attention to multi-head attention. Multi-head attention is actually what's used in the transformer architecture from the original paper, and it's also what's used in most other modern transformer architectures. So previously, when we introduced the self-attention mechanism with learnable weights, we also introduced three weight matrices, UQ, UK, and UV. We then use these weight matrices to compute the query, the key, and the value sequences. So to understand multi-head attention, let's actually just add an index here and call them UQ1, UK1, and UV1. So multi-head attention is a natural extension of self-attention where we have a stack of H such matrices. So now instead of just using UQ1, we now also have UQ2, UQ3, and UQH, where H is the number of attention heads. And yeah, correspondingly, we have the same for UK and UV. So as a brief recap of the single-head self-attention mechanism that we covered in the previous video, our input looks like as follows, where we have an embedding matrix X that has as the number of rows the number of input tokens, and the columns are the embedding dimension. So X here represents the whole embedded sentence. And then we multiply that input sentence with the matrices U to obtain the values, the queries, and the keys. So this would look like as follows for single-head attention, which we covered in the previous video. So essentially for each input in the embedded sentence, we will obtain a context vector. And for example, if the input consists of 10 words, the output will consist of 10 context vectors. So while attention can be carried out to generate all context vectors all at once, let's actually focus on the second element for simplicity now. So if we have the second input element here, we carry out the following multiplications to obtain the second context vector specific to this second input element. And this is again for single-head attention, which we covered in the previous video. When we go to multi-head attention, it's exactly the same computations, except now we have H attention heads. So for simplicity, you can think of it as having multiple convolutional filters to generate multiple output channels, like we discussed in Unit 7. So when we go from single-head attention to multi-head attention, we are essentially just stacking up multiple weight matrices and carry out these computations in parallel now. So for example, if we still focus on the second input element here, instead of obtaining a single context vector, we now obtain three different context vectors. The three context vectors are different here because they involve different weight matrices for Q, K, and V. So now that for each input element we receive three output vectors, what do we do with these vectors? Actually, what we do is we just simply concatenate them into a combined representation. So earlier we mentioned that transformers are a many-to-many architecture where we have one output token for each input token. However, with the multi-head approach here, if we have three attention heads, what will happen is that for each input element we will have three context vectors. So how does that work in the context of this many-to-many approach? So in order to achieve this one-to-one mapping, what we do is we first concatenate these output vectors and then put them through a linear layer to again squeeze them into one single output vector. So again, while we temporarily have multiple output vectors, multiple context vectors, we go back to this one context vector per input token. Yeah, and this is in a nutshell how the multi-head attention works in the context of transformers. And like I mentioned before, it's still the most popular attention mechanism that is currently used in modern transformer architectures. However, the transformer also consists of some other interesting elements which we haven't discussed yet. So in the next videos, let's also understand the other parts of the transformer architecture.